We're finally ready to determine the last of the coefficients for this Fourier expansion of this square wave. In the previous videos, we've determined that the a sub v value is 0, the a sub n values are 0 for all values of n, and we have now just to calculate the coefficients in front of the sine terms. We saw before that we can calculate those by taking this function and multiplying it by the sine of k omega naught t and then integrating over the period. So let's go ahead and do that. Inserting in for f of t, our piecewise continuous, this then becomes b sub k is equal to 2 over t times the integral. Now we're going to be breaking the integral up over two parts, from 0 to t over 2 and from t over 2 to t. So we'll have from 0 to t over 2, the value in this interval is just v sub m times the sine of k omega naught t dt, plus the integral from t over 2 to t of negative v sub m sine of k omega naught t dt, and close that parentheses. Now, let's go ahead and do this integration, realizing that there's a v sub m term on both of them, and let's give ourselves a little bit more room. We'll come over here and we have then 2 times v sub m over t. Now, integrating the sine. The integral of the sine is negative cosine. So I'm going to have a negative. Now this is the sine of k omega naught t, so we're going to kick out a 1 over k omega naught. And then we've got cosine of k omega naught t evaluated from 0 to t, that's a capital T, over 2. Now we've already pulled the v sub m out in front. I'm left with a minus sign, so it's going to be minus, but the integral of the sine is negative cosine, so I'm going to get a negative there. I get this 1 over k omega naught term out in front again, k omega naught times the cosine of k omega naught t. This time it's evaluated from t over 2 to cap t. Let's square that off. Now we need to evaluate these two terms at their limits, and at the same time let's replace omega naught. Recall that omega naught is equal to 2 pi over t. So we'll have then, again allowing ourselves a little more room because this is going to start to expand, we've got then 2 v sub m over t multiplying this whole mess, which is negative 1 over k 2 pi over t times this thing evaluated at the upper limit minus this thing evaluated at the lower limit, or the cosine of k 2 pi over t evaluated at t over 2 minus the cosine of k 2 pi over t evaluated at t equals 0 plus 1 over k 2 pi over t times this thing evaluated at both limits, cosine of k omega naught again is 2 pi over t. At the upper limit is cap t minus the cosine of k 2 pi over t at the lower limit, or t over 2. Close that off. Close that off. Now we've got some canceling that we can do. This t cancels that t. That 2 cancels that 2. The cosine, this is just the cosine of 0. In here I've got a canceling that and that. This t cancels that t. This 2 cancels that 2. And let's clean this up again. We've got this 2 v sub m over t multiplying this entire thing. Well, both of these two terms have a 1 over k 2 pi over t. So let's bring that on outside. I've got 1 over k 2 pi over t. And that leaves us then with a minus multiplying both of these terms. Well, what's left here is cosine of k pi. So it'll be a minus cosine of k pi. Then I've got this minus multiplying that minus, which gives me a plus the cosine of 0. Now we've factored this term out here, and we're left with plus, this is the cosine of k 2 pi, cosine of k 2 pi, minus the cosine of k times pi. Now, this term here, cosine of 0, that is always 1. The cosine of k times 2 pi, where k is an integer, that's the cosine of 2 pi, 4 pi, 6 pi, 8 pi. That's always equaling 1. But these two terms here, we've got minus the cosine of k pi and minus the cosine of k pi. Those are the same term. We only need to look at one of them. But we've got, when k is 1, we have the cosine of pi, which is negative 1. When k is 2, we have the cosine of 2 pi, which is a positive 1. When k is 3, it's cosine of 3 pi, which is a negative. So let's look at these two terms here for when k is even and when k is odd. When k is even, we've got the cosine of 2 pi. Well, the cosine of 2 pi is 1, but I've got a minus sign there. So when k is even, this term is always going to be a negative 1. Similarly, this term here is a negative 1. Now, these are 1 for all values of k, so for k even, that's going to be a 1 and a 1, plus 1, plus 1. This term inside the brackets, then, when k is even, gives us a negative 1, plus 1, plus 1, negative 1. That gives us a 0 here. It doesn't matter what this is out in front. We're going to get, just when k is even, the b sub k terms are 0. Now, when k is odd, it's just a little bit different. Let's first of all clean this up a bit. I've got a t that cancels that t there. I've got a 2 that cancels this 2 here. So this term now becomes v sub m over k pi. That's just this coefficient out here in the front. It's going to be multiplying. Now, when k is odd, k would be 1. Cosine of pi is negative 1. Negative times a negative is a positive. When k is 3 pi, the cosine of 3 pi is negative 1 times negative is a positive. K is 5. Cosine of 5 pi is negative. When k is odd, this cosine term is always going to be negative. Multiplied by a negative makes this a positive 1. This term here is positive 1 for all values of k. This term here similarly is positive 1 for all values of k. And we've already pointed out that this term is the same as that term. So it's going to be a plus 1 there. 1 plus 1 plus 1 plus 1. This term inside the brackets gives us a 4 multiplied by v sub m over k pi. b sub k then equals 4 v sub m over k pi when k is odd. And as we've already pointed out, the b sub k's are 0 for k even. So rewriting our results for the previous page, we now have the expressions for the b sub k terms. So when k equals 1, 1 is odd, b sub k, or b sub 1 we should say, is going to equal 4 times v sub m over k equals 1, so it'll be 1 times pi. For k equals 2, b sub 2, well, k is even, it's going to be 0. K equals 3, b sub 3 is going to equal 4 v sub m over 3 pi. K equals 4, b sub 4 equals 0. Let's just do one more. K equals 5, b sub 5 is going to equal 4 v sub m over 5 pi. So we can now write the Fourier series. Our function v of t, that piecewise continuous square wave, is going to equal, well, the a sub v terms is 0 for a sub v. It's going to add in then the 0 for all of the a sub n terms, and then we have the b terms, well, our B1 is going to be, so V sub t is going to equal 4V sub m over n equals 1 times pi times the sine of n pi, well, n is 1, or I'm sorry, sine of n omega naught t, it'll be the sine of 1 times omega naught t, plus when k equals 3, well, first of all, k equals 2, it's going to be a 0 times the sine of 2 omega naught t. Then the next non-zero term is b equals 3, or k equals 3 for b sub 3. So I'll have then plus 4v sub m over 3 pi times the sine of 3 omega naught t, plus this last one here, 4v sub m over 5 pi times the sine of 5 omega naught t plus, and it just goes on forever. Let's say it in words then. That function v of t can be written as, in this case, a single infinite sum of terms involving what we're going to refer to as the odd harmonics. This is the first harmonic, or the n equals 1 harmonic. This is the third harmonic, or n equals 3 harmonic. This is the fifth harmonic, the seventh harmonic, and so on.